Okay, in this video I want to talk about the quantum numbers and energy level diagrams. And most specifically here I want to talk about the actual energy associated with the different orbitals or the different electron shells around an atom. So remember the principal quantum number, which we call n. Oh, there we go, we're working now. Sorry about that. Sorry, the principal quantum number that we call n refers to the main energy level or the size of the orbit. So n equals 1, n equals 2, 3. As we go up, we go to higher energy levels, right? So n equals 1 is the smallest, and that's the lowest energy. And n equals, say, 3 would be larger and have a larger energy associated with it. But that's not the only thing that tells us about the energy level of the orbit. The secondary quantum number, which is also sometimes called the angular momentum quantum number, also gives us some information about the energy of the orbit. A sphere, so the S level, can't really rotate, or you don't notice when it does rotate, and so it's given an angular momentum quantum number of 0, which means basically there's no energy associated with this orbital rotating or spinning. However, the L equals 1, the pi-shaped orbital, or the dumbbell orbital if you want, if that spins, we're going to notice. And so there is energy associated with the spinning of this orbital. In fact, as we go up to L equals 2 and L equals 3, we have more and more energy associated with the idea that these orbitals, while they may not be bigger, which would make them higher energy, they're spinning, which gives them a secondary source of energy. So the principal quantum number is still the principal measure of energy, but the secondary quantum number, or L, also impacts the energy of the overall orbital. What this means then is that the energy doesn't just go from smallest to largest, as according to n equals 1, 2, 3, but that there can be some tricks where the energy associated with the L, or the angular momentum, can cause the orbitals to have energies that don't fill in that specific order. So let's look at it and let's just get the actual values. So n equals 1, L equals 0, and that's the only one for n equals 1, right? Because remember, our restriction on this is that it goes from 0 to n minus 1, is our lowest energy shell. Our other notation for this is the 1s shell. That is the lowest. And if we go n equals 2, L equals 0, that is the second lowest. It has a bigger size, but it doesn't have any spinning energy, so that is our second lowest energy, 2s. If we go n equals 2, L equals 1, which is now allowed according to our restriction, or we say at the n equals 2 level, the shell is now big enough to take on the dumbbell shape. That has a slightly higher energy because now it has a bigger size and a little bit of spin. That's our 2p. N equals 3, L equals 0, has our next highest energy. It's a little bit bigger, but it's not spinning. So that's our next energy up, and that's our 3s shell. Then n equals 3, L equals 1 is higher energy than that because now we have both the bigger size and the spinning. So that's our 3p. And this is the first time something strange or something unexpected is going to happen. The question is, we're going to have two orbitals to choose from here. We're going to have n equals 3, L equals 2, which might seem like it should come next because we are within that restriction, or n equals 4, L equals 0. And what happens here is that n equals 4, L equals 0 is actually lower energy than n equals 3, L equals 2. The reason here is that the spinning energy, the change for spinning energy, is bigger than the change to go from 3 to 4. So this is bigger, but it has no spin or no angular momentum. This is smaller, but it has angular momentum. And so this one happens to be slightly higher energy. So what that means then is we fill our first shell, we fill our second shell, we fill most of our third shell, and then weirdly we go to our fourth shell before we finish filling our third shell. This is reflected in our periodic table. If you recall the shape, if we consider the top row to be filling the first shell, then we actually have 2 rows of atoms, 2 columns of atoms that have 8 electrons. So this would be like the 1s, and this would be like the 2s, and these guys are like the 2p's. And then we get the 3s and the 3p, but then we actually get the 4s before we get this big long block of 10 electrons associated with the 3d. And then we go on with filling the 4p. So we can see this in our periodic table. We can see that this 3d shell versus 4s, this 3d shell actually comes after the 4s, and this is why. While it's a smaller shell, it actually ends up being a higher energy because it doesn't just have energy from the size of the shell, but also it takes into account the spinning of the shells themselves to create a secondary energy associated with the angular momentum. There's a trick then, instead of going through every single one of these and figuring out exactly how they're going to fill, there's a trick we use, and we use this notation when we're using this trick, to know the order of energy or the order in which electrons fill when they're filling these orbitals. We start up on our upper left-hand side, upper right-hand side, and we make arrows going through this way. So we can see the 1s fills first, and then we would see that the 2s fills, and then the 2p and the 3s, and then we would have the 3p, and then the 4s. So there's our first weird one where the 3d came after. And then we would go 3d, 4p, 5s. So 3d, 4p, 5s. And then we could go, I'll just go up to 6s here. And then we would go 4d, 5p, 6s. And so that's the order of the energy of the actual electron shells, and that's the order that electrons fill. Let's recall then that S, since it only has the one orientation, gets 2 electrons, so that would get 2. That goes for all of the S's. P's, with their 3 orientations, ML equals -1, 0, and 1, can take a total of 3 times 2, 6 electrons. So we could put 6s here to say how many electrons can fill in those spots. And Ds, with their 5 orientations, can take 5 times 2, 10 electrons. And that gets us how many electrons can go in those different spots. All of this information was built into our periodic table, and we can see it where we end up filling the 5s, and then the 4D, and then the 5p. We can see this, or we can see the energy level of the different orbitals simply by the structure of our periodic table. I think I'm actually going to pause at this point and come back and talk about energy level diagrams in a secondary video, because I think this has been enough for this video. And so we'll do that in a second.